to the second week of the Introduction to Data Science module. In this lecture video, I'm going to be having a look at this WQ Algorithms notebook. So at this point, we've talked a bit about basic Python syntax, kind of the fundamentals of programming and program flow. We've also talked about some of the primitive data structures available to us in Python. And today we're going to turn again to kind of fundamental computer science concerns and think about not how we write effective code in Python specifically, but how do we come up with effective solutions to problems generally. So a computer program, of course, consists of a set of lines of code that the processor executes in a specific order. But often, these programs solve some kind of well-defined problem. Often that can be decomposed into simpler problems, often of a sort of mathematical nature. And our technique for solving these problems, the plan for solving these problems, is called an algorithm. The algorithm is sort of the solution to a problem that we then implement in a programming language to create a computer program. So for instance, there are algorithms for calculating prime numbers. There are algorithms for factoring integers. There are algorithms for conducting search. There are algorithms for sorting. So, for instance, sorting algorithm on Wikipedia, and there's a lot of information here about different sorts. Simple sorting algorithms that don't work very well in that they are slow. More efficient sorting algorithms. And there's a lot of actual kind of mathematical theory that goes into these algorithms, which you will discover if you actually read through this page just on sorting. And of course, algorithms is a huge portion of computer science and very mathematically inflected. But we're going to talk about a few kind of concerns that should be in our mind when we're solving problems using algorithms by writing programs. So again, an algorithm is just a sort of set of instructions to solve some problem. You could have an algorithm to make a sandwich. These recipes for cooking beans and baking bread that I showed in the previous lecture on data structures, those are all algorithms. Just the algorithms we'll be talking about will be translated into computer programs. So what are these concerns I've talked about? So they have to do with resources. We live in a world where resources are limited. We don't have infinite of basically anything. And most significantly, you and I don't have an infinite amount of time available to wait for solutions to our problems. So the first concern we'll consider is computational complexity, meaning how many instructions do we need to execute to solve our problem? Because if every instruction takes, say, a microsecond to execute, then the number of instructions that we need to execute is going to directly determine how long our program takes to run. If we write a program that makes 1,000,000 steps and each step takes a microsecond, then on the whole it takes 1 second. Not a big deal. But if it takes 100,000,000 steps or 1,000,000,000 steps, now we're waiting a couple minutes or 10 minutes for our computation to complete. So we'll consider how many steps are needed to complete an algorithm or complete a computation. We'll also consider how much memory do we need? How many bits of information do we need to store in order to complete a task? If I have, for instance, 2 lists of people, and I'm considering all the different pairs of people that I could make, then if I am going to write those out and remember them by like storing them on a piece of paper or something, then if I have n people in each list, then I'm going to need n squared memory in order to write out all the possible pairs. So we'll talk about that. And also we'll talk a bit about input-output. So how many reads and writes do I need to make to disk? How often do I need to send information over a network? Because these operations tend to be somewhat slow. In terms of computing hardware, moving information from memory or processor cache to the processor is very fast. But moving information from disk or from the network to the processor tends to be fairly slow. Usually something like 100 to even maybe 10,000 times slower. So these are the kinds of concerns we'll be thinking about, and we're going to try and address these in the algorithms that we write for solving problems, or the algorithms we use for solving problems. Now, before we jump into the meat of these considerations, I want to introduce a notation that will help us discuss how much time an algorithm costs, how much memory an algorithm costs, those sorts of things. And it's called Big O notation. O stands for order. So we might say an algorithm takes the order of n time, or n squared time, where n is the size of our input. So if I have a list of n numbers and I want to compute their sum, I'm going to need to take n steps to do that. So n steps, n time, order n time. So here's an example of that. We have a function that sums the numbers between 1 and n. So we input n and sum from, 0 up to n. And we just increment the sum as we generate new numbers. And this is order n because we do n operations. We only care in Big O notation about the leading term. We don't care about coefficients. Like if this algorithm had more steps in here, then we would be doing 3n operations, but we don't care about that number 3. We only care about the growth in time, the growth in the length of time to complete as a function of n. So we call this order n, even if there are more instructions. And we also don't care about the fact that like we have some operations here and here, where we might say, oh, this is n plus 2. We don't care about the plus 2. We only care about the leading dominant term in the length of time as a function of n. We could also, so can we do better than this, right? Like, if I give you a list of numbers, it's going to take you n steps to sum up those numbers, because you sum up the first two, and then you add the third one to that, and the fourth one to that, and you have to go through each number and add them all together. But when we're dealing with numbers between 1 and n, we actually can solve the problem directly. A mathematician named Gauss worked out this sum and found that the sum is equal to n times n minus 1 divided by 2 for any n. So rather, we could propose another algorithm based on this idea, or this is the algorithm really. Here's another algorithm for solving this problem, and we implement it in this sum Gauss function. And now we no longer have n steps. We have exactly one step. So we would say this algorithm is order 1 time. No matter how big n is, our solution involves executing the exact same number of steps. It's a constant. So we also may call this constant time. So the number of steps I make does not depend on the size of the input. And these functions do the exact same thing. They give the exact same answer. So what's happening here is for every n between 0 and 100, I compute the sum using our first function, and I compute the sum with the second function, and I assert they are equal. I can't remember if we've used assert before. The purpose of assert is that assert true will do nothing, assert false will throw an error, an assertion error. So assert always is followed by some Boolean expression, and if that Boolean is ever false, then the assert will throw an assertion error. So assert is like a big attention-getting way to check if something is true. So let's actually demonstrate to ourselves that these functions really take a different amount of time. So we will compute this sum, changing n, like we just did, and we're going to measure the length of time it takes for the computation to complete, and then we'll make a little graph of how long it took. So now we're running this cell where we have a compute function that let's see here. we're going to perform the sum many times, n averages times. We give the function for computing the sum, and n, the number we want to sum up. And we're going to go through and compute the sum of 1 through n. So that's right here. And we do this n averages times. And we compile a list, of times, the length of time it takes to compute. And then we compute the average time. So let's unroll this a little bit to see how it works. So time.time gives us the number of milliseconds since, nanoseconds, or something like that, since a date called epoch, January 1st, 1970, midnight. So it's a common representation of time on Unix-based operating systems. So we see this time.time keeps changing as time moves forward. So we set the current time in a variable ts, and then we say use sum num with sum n, let's say 1,000, and then we compute the amount of time that has passed. So for example, so let's see here. I'm not sure exactly what units these are in. I think what the interpretation is, my interpretation of this comment is it took 0.2 milliseconds for us to compute the sum of 1 through 1,000 using this sum num function. And we can see each time we do it, it takes a different amount of time. Sometimes it's half a millisecond, sometimes it's a third of a millisecond, sometimes it's a sixth of a millisecond. So we do this quite a few times, n averages times, and then we simply take that average. So, all we're doing here is n averages equals, say, 100 for blah in range n averages. And what I'm doing right now, I feel is a very good strategy anytime you want to try to understand what a function is doing. Try taking it apart and executing it in little bits like we were. So is that right? So the average amount of time it's taking to run this function we see is like quite a bit more stable. Rather than jumping all over the place, it's coming around 0.035 to 0.04 pretty consistently. So before we were seeing changes of like 100 or 200% every time we ran it. Now we're seeing changes of like maybe 10%. And if we increase the number of averages, that number becomes even more stable. So we're just trying to get a really good idea of how long it takes to run this function. So that's what this compute function does. So we're going to do 100 averages And we're going to compute the sum from 1 through n, for n from 10 up to 100,000, taking steps of 5,000. And we're going to do it both for sum num and sum Gauss. We've actually already done that. I already ran this. And we can plot the amount of time it takes for both of those. And we see as we increase n, sum num takes an increasing amount of time to compute the sum. And it's linear, order n. So it's linear in n, the size of the input. Meanwhile, the Gauss method takes a constant amount of time, no matter how big n is. It always takes the same amount of time. So order n, linear, order 1, constant. The idea here is, the amount of time, t, that it takes to compute the sum is something like a times n squared plus b times n plus c. Something like this. In general, it could be like any polynomial or any function of n. Here, neither of our algorithms have an n squared term. Sum numbers has a linear term. We see that it's growing linearly with the size of the input. So we might say like sum num t prop 2 n. And then the Gaussian version we see takes a constant amount of time. So it has no linear term. So this is the kind of analysis that we've been talking about with big O notation. So this is a common thing to have to consider with algorithms. How long will it take? And we've already discussed this in the context of data structures. So one common problem we'll face is how should I store my data? So when we were discussing data structures, I was comparing lists and sets, or lists and dictionaries, and I mentioned that it's much faster to look up something in a set or a dictionary because we can calculate from the value itself exactly where it should live in memory. Meaning it takes order 1 time to find an element in a set or a dictionary. Whereas in a list, we have to look in every box. We have to look in each element of the list to see if our value is there. So it takes order n time as the list grows. If there's n elements in the list, it takes order n to find a particular element in that list. The trade-off that I mentioned in data structures is a set will usually take up more memory than a list. So we'll write a little function to find an element in a list, where we explicitly iterate over the list, and if I is in it, then we return true, otherwise we return false. So let's we're going to generate a random list of integers, or a list of random integers. You see it changes each time I run this. And we're going to compute, or try and see how long it takes to find an element in a list, iterating through the list. So I'm not going to delve into this code. It's very similar to what we had before for benchmarking or timing. We call timing benchmarking sometimes. The sum functions. I'm just going to go ahead and run this. And as the list grows in size, here we're considering larger and larger lists, it takes more and more time to find a particular element in the list. So this shows the linear growth, order n, for finding an element of the list. Let's now assume that the list is sorted. If the list is sorted, we can try a different approach using this information to our advantage to find an element faster. Now note that sorting takes n log n time. So there's a cost to sorting a list as well. We're disregarding that for now. We're assuming that our list is already sorted and we don't have to spend time sorting it. Of course, if we are searching a list many times, it may be worth it to sort once and then take advantage of the speed up in searching. So if I know that my list is sorted, then I can do a number of optimizations. The first thing I could do is I know that I'm going to encounter elements in increasing order. So if ever the thing I find in the list is larger than the thing I'm looking for, I can stop. So if I have a list 1, 2, 3, 4, 5, or let's say 1, 2, 4, 5, 6, and say I'm looking for 3. I look in the first spot, it's not there. I look in the second spot, it's not there. I look in the third spot and I see 4, and I say 4 is bigger than 3, so I know all the remaining elements will also be larger. I can just stop now. So that's the most obvious advantage we can leverage, knowing that the list is sorted. So this looks exactly like what we had before. We're iterating over the list and checking if that element of the list is what we're looking for. But now we have an early stopping mechanism if the element is larger than what we're looking for. So now I'm benchmarking this new version with this optimization. And it's somewhat faster. But it follows, or appears to follow, a similar linear trend as the original function. And that's because our algorithm still has order n operations. If we aren't going to, even though our list is sorted, we don't know if the thing we're looking for is going to be at the end of the list or at the beginning of the list. And as our list gets longer and longer, we'll still have to, in general, search, roughly half the list. And, if our list is getting larger, half the list is also getting larger. So this still takes order n time. But we can do something still smarter. What we'll do is implement what's called binary search. We're going to basically split up our list into pieces, and by splitting the list in half many times, or iteratively, recursively really, we're going to be able to very quickly find what we're looking for. So, for example, assume that we have this list, 1 through 11. And we want to check if there's 2 in the list. So the first thing we'll check is the middle, which is 6. And 2 is not 6, so we haven't found 2 yet. But since we know the list is sorted, we will throw away this half, and we'll keep only this half. And now we'll do the exact same thing. We look in this sublist 1 through 5, and we check the midpoint, which is 3. 3 is not 2, but we know 3 is bigger than 2, so we can throw this away as well. And now we have this sublist. There is no midpoint, so we'll choose the first element. Actually, element 1, which is equal to 2. So we've found 2 at this point. So rather than, iterating over the entire list, we are able to throw away portions of the list and very quickly narrow down to the element we were looking for. And it turns out that you can connect this with kind of a tree structure called a binary search tree. Where the number of levels in the tree is log n, where n is the number of elements in the tree. And so to find something, we just have to start walking down branches of the tree until we find it. And since there's n order log n layers, it's going to take us log n time to find that. So this binary search algorithm should take order log n time. So once again, here's an implementation of that algorithm. If ever we have an empty list, we haven't found what we're looking for, so we return false. Otherwise, we compute the midpoint. If the midpoint is the element we're looking for, then we are done. Otherwise, if the midpoint is larger, then we're going to apply the exact same technique, this binary search, to the sublist that is to the left of the midpoint. And if the midpoint is less than the element, we're going to apply binary search to the sublist that is to the right of the midpoint. By doing this, we find this binary search is quite a bit faster. It's not clearly a logarithm, say, but it's difficult to, we spent a lot of time trying to kind of get this to convincingly look like the functional shape it should have, but often there are extra considerations in the programming language that will mean that your time complexity isn't exactly how long your function takes to run. Nonetheless, we see it's much faster than what we were doing before. So by applying this order log n algorithm, excuse me, we were able to much more efficiently conduct our search. And this is the inspiration behind, in the IP Mini project, the last question, Civ, which asks you to develop an even faster method for calculating primes. So we're going to often try and think about how long does my algorithm take to run? What is its time complexity? Is it order n? Is it order n log n? Is it order n squared? Is there a way that I could reduce the time complexity and make this more efficient? One easy example is search. If we are searching for an element in a data set, it's always going to be faster, order 1 time, if that data set is in a set or a dictionary, than a list, where it will take order n time. There are additional techniques for other than just like coming up with better algorithms for improving time complexity. There are techniques like memoization, which shift the responsibility of kind of performing calculations from time to memory. So we can often trade between time complexity and memory complexity. So often, the reason we can make this trade is because we will be recomputing things in the course of computing a particular value. So for example, if we want to compute the Fibonacci numbers, we might have a recursive function that does that. So we know, of course, the Fibonacci sequence is f sub n equals f sub n minus 1 plus f sub n minus 2. And we can implement that in code quite easily by saying the Fibonacci number, or the nth Fibonacci number, is the n minus 1 Fibonacci number plus the n minus 2 Fibonacci number. But when we do this, we're going to recompute many things because to compute the nth Fibonacci number, we have to compute the n minus 2 Fibonacci number. Well, when we do that, we compute first the n minus 1 Fibonacci number and then the n minus 2 Fibonacci number, and in computing the n minus 1 Fibonacci number, we will also compute the n minus 2 Fibonacci number, because relative to n minus 1, n minus 2 is n minus 1. So we keep recomputing elements of this sequence over and over again if we take a recursive approach. In fact, we'll define here a function that keeps track of how many times we compute each element of this sequence. So if we are computing the fifth Fibonacci number, we compute the third Fibonacci number twice, the second Fibonacci number 3 times, the first one 5 times, and the 0th 3 times. And we can see in this tree structure how that breaks down. So we want to compute the fifth Fibonacci number, which means we have to compute the fourth and the third. Well, to compute the fourth, we have to compute the third and the second. To compute the third, we need to compute the second and the first. So we're seeing duplications throughout this process. We can implement this more efficiently by storing as we progress through this calculation, storing the result and only computing results if we don't already have the results stored. So for example, we would come through here and say, okay, to compute the fifth, I need to compute the fourth and the third. Before I compute the third, I'm going to continue down this way. So to compute the fourth, I compute the third and the second. To compute the third, I compute the first, the second, and the first. To compute the second, I compute the first and 1 and 0. So I know these things, and they give me this. I know this thing, I know this, so I can compute the third. I just computed the second, so I store that answer. Now to compute the fourth, instead of computing the second again and walking down here, I just look up my answer from before. And now I don't have to compute the second again, and I compute the fourth, and I don't need to compute the third because I just calculated that. So I'm just going to store the answers as I calculate them, and rather than recursively call the function all the time, I'm going to first try and look up the answer from what I've calculated in the past. And this cell shows that this problem gets really bad as the number n increases. The number of repeated calls starts to grow exponentially fast because this tree grows exponentially fast. N labels how many layers there are in the tree, and as the number of layers grows, the number of elements grows exponentially. We get 2 for each layer. So let's do this in a memoized way. So we're going to now call Fibonacci mem with n, the nth Fibonacci number to compute, as well as d, some data structure, which will turn out to be a dictionary. So we're going to check if we've computed the nth Fibonacci number, if it's in our dictionary d. If it is, we'll simply return that. We've already computed this answer. We can just look it up. Otherwise, we consider our base cases, what we looked at before. And if it's neither a base case nor in our dictionary, we'll go ahead and make the recursive call to compute that nth Fibonacci number. And when we get the answer, we'll add it to our dictionary. We'll remember it. And this is going to provide us a massive speed up. So the memoized version takes roughly 10 milliseconds to compute the 33rd Fibonacci number. Meanwhile, the recursive, non-memoized version takes 1 second. It's 10,000 times slower. Or no, sorry. It's 100,000 times slower than this memoized version. And they give the exact same result. It's purely a difference in
recomputing all these answers. So this is a massive speed up. In fact, when I was describing walking through this tree and simply looking up answers, we basically were able to walk down just one branch of the tree and only sometimes split off to the side. But mostly we walked down one branch and split off to the side only a couple times, which meant that we took a algorithm that takes an amount of time exponential in n, right? There's an exponentially large number of things as a function of n to compute here, and we made it into something that's almost linear in n, where we just walked a straight line down the tree, 1, 2, 3, 4, 5 steps. So this is a massive speed up, exponential to linear. There are some exercises for you, asking you to write a recursive function for factorial, and also consider, would memoization make this function faster? So I'm actually going to post that to the discussion board, or I will. Yeah, I'll do it now. Why not? So let's see. How did I ask this again on other cases? Set versus, it's not on this page. There we go. Exercise from, okay. So you can share your thoughts in this, in response to this question. I'll include this one as well. Okay, now, memoization, as I mentioned, involves a trade-off in terms of memory. We had to construct this data structure D, a dictionary, that stores answers so we can look them up. So since we are memoizing all the elements of the Fibonacci sequence up to the nth number, we require order n memory. We have n Fibonacci numbers to remember, to memoize. So we can take exactly the same approach to considering memory costs as we can to time costs. One simple comparison or like one of the simplest comparisons we could do is considering two functions that compute a sum. One that the sum of the numbers 0 through n, one that constructs a list of those numbers, and one that computes the sum iteratively. And they give us the same answer, but this one is going to construct a data structure that has every number 0 through n. So it's a list of length n. So it's going to take up order n memory. We have n elements to store in memory here. This approach, on the other hand, we just iteratively compute the sum. We have two variables, just two numbers, and we just increment them as we iteratively compute the sum. So no matter how big n is, we only store two numbers in memory ever. 3 if you count n itself. So this is constant in memory. Linear in memory, order n. Constant in memory, order 1. So hopefully I've impressed upon you that you often want to give some thought to what algorithm you'll use to solve a problem, because if you choose poorly, it will cost you quite a lot of time. And the difference between microseconds and 1 second might not seem very long, but when you are computing something a million times, 1 microsecond times a million is 1 second. 1 second times a million is a million seconds, which is 277 hours or 11 days. So the difference between waiting a microsecond and waiting 1 second might not be significant, but often we'll want to repeatedly compute something, and then if the cost difference is really 1 microsecond compared to 1 second, if we pay that cost many times, then it can really add up to something we care about. Not only should we think closely about algorithms, but also data structures. So many data structures are closely tied to particular algorithms. So, for example, if we want to find the largest elements in a particular data structure, we could compile a list, sort it, and then take some n elements from it, like the largest n. But we could also build what's called a heap. And a heap can add elements in a sort of sorted way in log n time. So the heap is actually very closely related to binary search. So it's very common that data structures will be connected to particular algorithms, like this connection between binary search and heaps. There's also connections between depth first search and which is recursive, and stacks, breadth first search and queues. I'm not going to get into a ton of detail here, but you may, if you are interested in computer science, and are curious about these connections between data structures and algorithms, there's a really great website called interactivepython.org that has several books on it. There's one called Problem Solving with Algorithms and Data Structures. This is a terrific book. I highly recommend it, and it involves great code examples in Python, and it's a nice introduction to computer science, and gives plenty of these examples of connections between data structures and algorithms. I'll also post this exercise to the discussion board. Okay, so that wraps up the first lecture of this week. The next lecture, we'll be looking at this WQ Pythonic notebook.